Hi there. Today we're going to learn about something called electron configuration. And as of this year, 2023, this is starting on page 8 of your notes. So once you're ready, let's get going. If you watch this video and you feel like you still need some extra help, these videos are linked in the slides that you can find on our HyperDoc through Schoology. So first up, what is configuration? Configuration is how something is arranged. So when you play Battleship, your goal is to figure out the configuration of your opponent's ships. You want to figure out where they are and how they're oriented. So that is what configuration means. When we talk about electron configuration, this tells us the location of electrons in orbit around the nucleus of an atom. So the location is the configuration of the electrons. Now, it's actually what determines how an element is going to behave chemically. So it's not an overstatement to say that electron configuration is very important. It is everything to chemistry. Today we're going to learn 3 different ways to show electron configuration. The first way is called orbital notation. The second way is called electron configuration notation. And the third way is called shorthand notation. We're going to learn all 3, and the first one takes the longest, and then they get easier and faster as we go. Before we can really get into the skill of electron configuration, we need to understand a little bit more about how electrons exist in the atom. So first, we are understanding that electrons don't just exist in what's called shells or levels around the atom. There are also subshells that have smaller parts called orbitals. So in your notes, I want you to draw what I draw over here in white. It's just a couple of words. So first off, we might have what's called an energy shell or a level, but that is not the end of the story. For instance, we might have level 3, but within level 3, like we see in the picture, level 3 is made up of 3 rings itself. So the shell or the level is broken up into smaller parts called sublevels. Now, sublevels are going to have funny names like 2s or 3p. More on that in a minute. And then subshells also get divided into smaller parts, and those smaller parts are called orbitals, and they hold 2 electrons. That concept right here is very important because all of these words I will be using today. So make sure you have that written down and know that the shell is the biggest of these terms here. Shell is the biggest, and it's going to be energy level 1 or 2 or 3. And then orbital is the smallest. And it is a little home for electrons, and it holds 2 electrons. This picture here is showing us very specific information about energy levels and the subshells within them and the orbitals within them. This part of the video is very crucial, even though there's not a lot to write down. So try to follow along with my pointer. So first up is energy level 1. Energy level 1 is very simple. It is made up of 1 subshell, and that's represented by this curved line here. And that subshell is called 1s. It's just a name, go with it. Within that subshell is 1 little home for orbitals, or 1 little home for electrons, which is this circle that has 2 dots in it. So I'd like you to label on here, because you have this diagram in your notes, that whole thing there is called level 1 of the atom. Next, I want you to circle where it says 1s, and we're going to label that a subshell. It's also sometimes called a sublevel, and subshell and sublevel mean the same thing. Finally, circle the circle with 2 dots in it and label that an orbital. And remember, an orbital holds 2 electrons. All right, so level 1 is very straightforward. It's one subshell with one orbital. But let's look next at level 2. Level 2 is higher in energy. And we see, because it has two curved lines in it, it has two subshells. So the subshells, just like the first level, are the labels 2s and 2p. The s subshell, just like 1s, 2s contains one orbital. 2p is a bigger subshell though, and 2p contains 3 orbitals. So let's kind of look for patterns as we move on and look at level 3. Level 3 has 3 sublevels in it now. So I'm going to circle level 3 with my purple highlighter. And we see that level 3 has 3 sublevels. I'm going to highlight their names in blue. 3s is this subshell right here. 3p is this subshell right here. And 3d is this last subshell right here. A pattern that we see, and I have a lot of notations here, but try to watch for the green notations. All of the 1s levels are structured the same. All of the 1s sublevels have one orbital. And that holds true in the 4th level also. The 4s subshell has one orbital. Okay, I'm going to erase a lot of my notations here so that we can focus on something, a pattern. Next in green, no, let's do blue. I'm going to highlight all the p sublevels that I see. So here's a 2p sublevel. Remember, it had 3 orbitals. The 3p sublevel had 3 orbitals, that's 6 electrons. And the 4p sublevel had 3 orbitals, that's 6 electrons. So I'll say it again. All of the p-type sublevels had 3 orbitals, which can hold 6 total electrons. All right, so we're kind of seeing the structure here that energy levels like that can have smaller subshells, which are 3s, 3p, and 3d. And then within those subshells, we have orbitals, and the orbitals are the homes for 2 electrons. So I'm highlighting some orbitals here. Orbital is a home for 2 electrons. All right. Using that vocabulary, we are going to look at the different types of orbitals that exist. The type of orbital depends on what type of subshell it's in. So first off, I'm going to circle in black. I'll make it bold. Some information. So first up, S-type subshells. So remember 1s, 2s, 3s, etc. They have one spherical shaped orbital and they can hold 2 electrons. So any S-type subshell has one orbital. It's represented by that red sphere, and that means that it can hold 2 electrons. Let's look at the P-type next. P-type subshells, I'm going to highlight this in pink, that might stand out more. P-type subshells have 3 orbitals. They can hold 6 electrons. So a P-type sublevel is going to look like this yellow drawing over here. Each of these things that I'm putting a check mark on are an orbital. So there's 3 orbitals, and because an orbital can hold 2 electrons, that is going to hold 6 total electrons in a P-type subshell. Notice their shape is not a sphere. We call that a peanut shape. Next we have D-type sublevels. So D-type sublevels have 5 orbitals in them, and their shape, we call it a double peanut because it's kind of like 2 of the P-types crisscrossed. So D-type subshells have 5 orbitals. That means that they can hold 10 electrons. The final type is F-type. We're not going to encounter these very often. F-type subshells have 7 orbitals. And because they have 7 orbitals, that means that they can hold 14 electrons. So one thing that you might be wondering is, how on earth am I supposed to know what these sublevels are? Like, what sublevels even are real? What sublevels exist in the atom? And more importantly, what's the configuration of the electrons in them? How do the electrons go in? Well, the good news is the periodic table is going to tell you the order that the sublevels fill. So follow along, find this in your notes. You are going to read this periodic table like a paragraph, meaning that you are going to start at the upper left and you are going to go across. So as we go across that first row, we see that the first sublevel listed, and I'll highlight it in pink, is called 1s. So the first sublevel that fills is 1s. Next, we would go to the second row. The second row of the periodic table, the first sublevel we come to is 2s. Remember, s-type can hold 2 electrons, and then we continue on. The next sublevel that we get to is 2p. And remember that 2p can hold 6 electrons. Okay, we finished the second row. Moving on, the next sublevel that we can occupy with electrons is 3s, can hold 2 electrons. And then moving on, we get to 3p, and it can hold 6 electrons. Let's go through one more row. Next row starts with the subshell 4s, which can hold 2 electrons. Continuing on, we get to a subshell called 3d, which can hold 10 electrons. And moving on, we get to 4p, which can hold 6 electrons. So this is how we know the order that we are going to fill the orbitals. Okay. 3 quick rules, and then we're going to get into the actual examples here. This is the rule for how electrons enter the subshells. And this rule we actually already talked about. The Aufbau principle says that electrons enter subshells of the lowest energy first. And we use the periodic table to determine the order they're going to fill. So, for instance, electrons are going to enter 1s, then 2s has to be filled, then 2p has to be filled, then 3s has to be filled, then 3p has to be filled. We have to go in that order. We are not allowed to skip around. That is the Aufbau principle. The Pauli exclusion principle has a complicated definition. No 2 electrons can have the same 4 quantum numbers, but I'm going to be very honest with you. I'm never going to ask you that in those terms. Instead, I want you to know the following definition. Each orbital can hold 2 electrons, and those electrons are going to move in opposite directions. They're literally moving in opposite directions around the atom. So we model that on paper by showing in an orbital, which we represent with a box, an up arrow and a down arrow to represent the 2 electrons moving in opposite directions. We are not allowed to put 2 arrows moving in the same direction, and we are also not allowed to put 3 electrons in a single orbital. So that's another no-no. The third rule for electron configuration is called Hund's rule. And this one says when electrons occupy orbitals of equal energy. So what that might look like, y'all, is, let me go back to the diagram that we studied longer. If you have the 2p sublevel, which is this level right here that I'm highlighting, there are 3 orbitals in that sublevel. But if we're putting, let me take the electrons out. So empty orbital, empty orbital, empty orbital. And imagine this stuff is not there. If we need to fill electrons in those orbitals, we are going to put 1 electron in each orbital before we pair them. So watch very carefully on that highlighted 2p section. My first electron goes in the first orbital. My second electron goes in my second orbital. And my third electron goes in the third orbital. I like to call Hund's rule the bunk bed rule, because if you had 3 people and 3 bunk beds, everyone's going to take their top bunk. No one wants to share a bunk bed with someone maybe you don't know. So you're going to take your own top bunk I like to think of bunk beds in a cabin at camp. If you have 3 people in a room with 3 bunk beds, and there's people you met that day because you just got to camp, everyone's going to take the top bunk of their own bunk bed. But what if somebody else shows up? The next person has to share. So the next electron has to share in the orbital. The next one has to share. And the next one has to share. So that is how we fill electrons in orbitals, and that's called Hund's rule. So in this example, where we're looking at the 3 orbitals here, the way that we would model that is our first arrow would be an up arrow, and we do a lazy arrow, we just do half. The second one would be in the next column, the next orbital, and the third one would be in the third orbital. After we have 3 electrons in the 3 orbitals, then we can begin to double up with down arrows, because remember, they move in opposite directions.